Hi everyone. So next we'll see the applications, like if you apply the Laplace transform, how to determine the transient behavior of the several linear lumped parameter circuit. Already we have seen this kind of analysis in the time domain analysis, transient analysis for the time domain circuit. The same circuit we can convert into the S domain, and with few steps we'll get the response in S domain. Then later we can get the time domain response also. Laplace transform also gives a similar kind of results like in the time domain analysis. First, if you see this circuit diagram, like it's a natural response of RC circuit. R and C, R and C are connected through a switch S, and the switch S is closed at t is equal to 0. The corresponding current flowing through this loop is small I. Assume initially the capacitor is charged with capital V naught voltage. And what is the first step is? The first step is you convert this time domain circuit to the S domain circuit. I'll go with the series representation of this capacitance, then later I'll go with the parallel representation. So your small, when switch is closed, if you convert that time domain circuit into the S domain circuit, the capacitance, already we have seen this capacitance representation in series form. How do we convert this capacitance into the S domain? C will become 1 by Cs. In series with that 1 by Cs impedance, voltage source V0 by S is connected in series like this. The capacitance series representation is S domain is nothing but C become 1 by Cs plus V0 by S. That's what we have seen in the previous class. Small I will become capital I of S. Small v will become capital V of S, and R as it is constant, same capital R only. As a first step, convert into the S domain equivalent circuit. Then second step, apply the KVL to this loop. When you apply KVL to this loop, minus 2 plus V0 by S is equal to 1 by Cs into I of S plus R into I of S. If you cross multiply and simplify it, you'll get the I of S as C into V0 by 1 plus RCS. But as you don't have the direct inverse Laplace transform for 1 by RC, 1 by 1 plus some Ks, you can take that S coefficient always common, so that you'll get 1 by S plus some A constant, like that. You'll get it, so that it is easy to apply the inverse Laplace transform. So I of S is equal CV naught by RC, I'll take it constant, RC I'll take it out as a common, S plus 1 by RC, V naught by R into V naught by R is divided by S plus 1 by RC is nothing but I of S. Now you apply the inverse Laplace transform. This is the next step. If you apply inverse Laplace transform, V naught by R is constant, e power, if when you have 1 by S plus A, inverse Laplace transform is nothing but e power minus AT. Here A is nothing but 1 by RC, e power minus 1 by RC into T. Apply the Ohm's law and get the voltage across the resistor. V of t is equal to R into I of t. R into I of t, already we know this equation. R into V naught by R is nothing but V naught. V naught into e power minus T by RC is nothing but voltage across the resistor. So if you see the overall steps, convert into the S domain equivalent circuit, apply KVL, find out the response, apply the inverse Laplace transform and get the response in time domain. And the same circuit, I can replace the same circuit with the parallel representation also. S domain equivalent for the parallel circuit representation of the capacitance. Capacitance C will become 1 by Cs. If it is parallel representation, means independent current source of CV0 is connected in parallel. A resistor as it is. Already we have seen how to represent the capacitance in S domain in the previous class. You can go through that. So if you apply KCL at here, now apply KCL. When you apply KCL, CV0 is equal to 1 by Cs into Vs plus 1 by R into V of S. So if I simplify this, I'll get the V of S is equal to V0 by S plus 1 by RC. If I apply the inverse Laplace transform to this one, V0 is constant as it is, 1 by S plus A form. 1 by S plus A means e power minus AT, e power minus 1 by RC into T. It is similar to the series representation. You got V of t is equal V0 into e power minus T by RC in both series representation. solution and also in parallel representation solution. So what is v of t is equal? V of t is equal v naught into e power minus t by tau. I have replaced this RC with the time constant. Tau is equal to RC. That's why v naught into e power minus t by RC. In a similar way, if you see other problem like use of this Thevenin's equivalent circuit, find the Thevenin's equivalent in S domain by considering the circuit shown in figure. If I have the circuit like this, first what I have to do, I have to convert the circuit into the S domain circuit. Here voltage is constant, like a step. The step of 480, the voltage is there. If you apply the Laplace transform to the step A or step K, K by S, right? So that's what 480 by S, a resistor replaced with the same resistor value, inductor replaced with the LS. If initial current and initial voltage are 0, then inductor becomes L into S. Capacitor become 1 by Cs. So inductor L is equal to Ls. L is nothing but 0.002 into S. Resistor as it is. Capacitance 1 by Cs. 1 by C means 1 by 5 into 10 power minus 6. That can be simplified as 2 into 10 power 5 by S. Now you need to find out the Thevenin's equivalent. We need to find the voltage across this A and B terminal and also resistance seen through this A and B terminal. To find out the voltage across this A and B terminal, remove the capacitance. If you apply the voltage across this A and B terminal, this 60 ohms will not have any resistance. So drop across this 60 ohms is 0. You need to find out the voltage across this inductance. You know the total voltage, apply the voltage division rule. Total voltage into same impedance by total impedance. 480 by S into same impedance 0.02 into S by 20 plus 0.002 into S. If you simplify, you'll get it as 480 by S plus 10 power 4. To find out the impedance, like I said, you need to, in Thevenin's, voltage source need to be short circuit. These two are connected in parallel, that is in series with the 60. To find out the voltage resistance between this A and B. ZTH is equal to 60 plus 20 is parallel with 0.002 into S. If you simplify this, you'll get the ZTH also 80 of S plus 7500 by S plus 10 power 4. So now you know the VTH and ZTH, you can draw the equivalent circuit diagram. Replace that capacitance between the A and B terminal by having this voltage source VTH in series with the ZTH. Already we know the VTH and ZTH have replaced and capacitance as it is, what we have removed earlier. Now find out the capacitance current IC, VTH by ZTH plus, this I am assuming it as ZL, and simplify it. If you simplify it, you will get the IC as 6S by S plus 5000 square. I don't have direct inverse Laplace transform equation for this one, so I'll use the partial fraction and divide it into the two terms. You can assume that A by S plus 5000 square plus B by S plus 5000 to do that partial fraction and find out that A and B constant. On the left side, 6S by S plus 5000 square is equal to A by S plus 5000 square plus B by S plus 5000. And you cross multiply with that A and B constant and compare the S coefficients and constant coefficients, then you'll get the A and B values as minus 30,000 and 6. Now you know the inverse Laplace transform for the first term and second term. First term is like 1 by S plus C square. 1 by S plus C square is nothing but T into e power minus at. Here A is nothing but 5000. T into e power minus 5000 into T. 1 by S plus A is nothing but e power minus at. E power minus 5000 into T. Constants are kept as it is. If you want to find out the voltage across capacitance is nothing but IC into corresponding capacitance. IC into corresponding capacitance is nothing but 1 by CSR SC. So IC is equal to already IC value, you know, 6S by S plus 5000 square into capacitance is 2 into 10 power 5 by S. If you simplify, you'll get 12 into 10 power 5 by S plus 5000 square. This is constant. 1 by S plus C square is nothing but T into e power minus 5000 into T. In this way we can find out the capacitance current and capacitance voltage. If your objective is to find out the capacitance current and capacitance voltage through the Thevenin equivalent circuit, what you have done here, first step is you have converted the time domain circuit into the S domain circuit. We have replaced each individual element with the S domain representation. Then find out the VTH and ZTH. Redraw the circuit diagram, Thevenin equivalent circuit diagram, and then I find out the IC. Then apply the inverse Laplace transform to get the IC in time domain. In a similar way, voltage in time domain, from S domain to time domain. So this is all about this applications. Thank you.